Okay, we're going to do this the hard way. Hi. Recurrence relations. So we did this back in sequences and series. We talked about forming the next term in a sequence from previous terms. So we define our sequence based on the pieces in front of it. If we only need to go back a certain number of steps, that's fine. But we did this in a number of different models, something like population growth. So I could look at a bacterial colony, number of bacteria in a dish, and I could say, oh, we start with 100 colonies in our dish, and every hour the number doubles. Well, there's my relationship. It says, oh, we start with 100, and then for all n bigger than or equal to 1, just double the number before. This is not the most realistic situation. I mean, if I let this go on and on and on, what happens to the number of bacteria in my dish? And then I'm going to be in trouble because after, I don't know, 24 hours, there are more bacterial cultures in this dish than there is room on the entire planet on the beach. So it's not a very realistic model, but at the very least, it can be some simplified model. We could talk about a model like this. Now, this is one of the original recurrence relation problems written in a book called Liber Abaci, the book on counting, by a guy by the name of Leonardo. Leonardo, son of Bonaccio. Wait a minute, it's Italian. What's son in Italian? Fib. Leonardo Fibonacci, son of Bonaccio. This, as the problem is published, is based on rabbits. I start with no rabbits. A month later, I have a pair. Brand new rabbits were born. A month later, they are capable of breeding. Gestational period is 1 month. What happens a month later? Well, okay, my rabbits grew up. They can breed. What happens? Well, the end of the month, I still have one adult pair of rabbits. They get happy. What happens here? Those happy rabbits give birth to a brand new pair of rabbits. These are now newborns. They won't be adults and capable of breeding for a month. But these rabbits, these were already adults. They can go ahead and have another pair of babies. So they give birth to another set. So how many rabbits do I have at any given point can be modeled by this recurrence sequence seen here at the bottom, page 528. So I got a question for you. I want to wait a year. What's F12? I'll be here for a while figuring out, won't I? I could. The fact that I'll be here for a while figuring out bothers me. I want to get back to that. Questions about the idea? Depending on where you heard of this toy from, I've heard it called the Tower of Hanoi, heard it called the Tower of Brahma. You have a series of discs on a spindle. Simple rule, you're never allowed to put a larger disc on top of a smaller disc. Move them from this spindle to this one. Now, I've drawn 4 discs, but you could have more. 2, 3. This is 6, right? 1, 2, 3, 4, 5, 6, right? So, I'd like to know, how many moves does it take? Hn is the number of moves to transfer n discs from rod 1 to rod 3. Doesn't seem like all that hard a question, does it? I'm actually sure that the easiest way to build this formula is to do it in a recurrent fashion. So let's see if we can come up with some sort of recurrence formula like we did for the rabbits, like we did for the bacteria. How many moves does it take to move one disc? Just one. You pick it up off of spindle 1, drop it onto spindle 3. How about 2 discs? Walk me through the process. How many moves? Santino? How 2? But my goal is to move them all to this rod, right? And I'm never allowed to put the smaller disc on the lighter disc, on the bigger disc. So if this one is bigger and this one is smaller, I could move that, right? That's the small one. Then I move the big one. Then I move the small one back on. So that's a total of 1, 2, 3 moves. But let me think about the way I did this. I moved the middle one to the holding spot, and then I only had to move 1 disc. So I had to move 1 disc twice. I had to move it off and move it back on. And then I just had to move the bottom disc, right? So I can think of this as I moved the bottom disc once, but I moved the stack above it 1, 2 times. So I can say, oh, to get H2, that's 3 moves, but it's really 1 and twice moving the stack above it. I'm in the unfortunate situation I don't actually have a third coin, but I have a ring. So let's do it for 3. How do I move 3 discs? Don't give me the number. Let's work this pattern. if I could move those two here, I'd be okay, wouldn't I? Because then I could move this one, and then I could move those two here. Notice I know how to move two disks, right? I could move the small one on top of big one, I'm okay. So I move 1, 2, no, I do it the other way. I go 1, 2, 3. I move the entire disk now to spindle 2. Then I move the bottom, then I move them back. So it's, for 3 disks, H3 is 7, but it's really 1 plus 2 sets of 3. As soon as I know how to move, I need these really to be different sizes. That look different, that looks different. Right now they look like they're different sizes. 1, 2, 3, 4, 5, 6, 7. What am I going to do when I put a 4th disk in there? I'm going to move all 3 of these to a stick. That's going to take 7 moves. Then I'll move the bottom one, and then I'll move all 3 of those. So it's 7 moves, 1 and 7 moves. There's a recurrence pattern, no matter how many disks you have. The picture in the book is 6 disks. How many moves? That's actually right. How'd you get it? Right, because this will be 15. So the next one will be twice 15 and 1, that's 31. Then it'll be twice 31, 62, plus 1 is 63. The reason this is named the Tower of Hanoi or the Tower of Brahma, depending on which version you saw, is that it was invented in England in this time when everything in the Far East was mystical and magical. And the story goes that there's a temple in Hanoi with 64 solid gold discs, ranging from a meter across to a centimeter across. The priests in the temple move 1 a day. When the task is complete, the great cycle will have ended and the universe will be over. How long is the universe going to last? I want H64. I'm not doing this way. I'm not, it would be a pain in the ass to repeatedly keep going, wouldn't it? The question that is asked of most recurrence relations is, can I find a non-recurrence version of the formula? We call this a closed form. So the question is, how can I find a closed form for this formula? And I think I can do it from here. Let me think about the way, Blaze, the way you told me to get H5, right? H5 is 1 plus 2H4. Yes? But H4 is 1 plus 2H3, isn't it? Keep going. I'm recursing all the way down. Wait a minute. What's H1? 1. That's not anything I need a formula for anymore. Wait a minute here. I've done my recursion all the way down to my base case. Gee, this sounds just like induction, doesn't it? I'm going to get 2 times a 1. I'm going to get a 2 times a 2. I'm going to get a 2 times a 2 times a 2. And a 2 times a 2 times a another 2. Chapter 2, section 4. What kind of a series is this? This should be on your formula sheet for the second exam. It's actually a geometric series because I'm adding, right? Which means I have a formula for the sum of a geometric series. The formula for the sum of a geometric series is that you take one more power. Minus the original A divided by the ratio minus 1. Wait a minute, what's the bottom of that? That's just 1. What's 2 to the 5th power, computer science people? 2, 4, 8, 16, 32. Minus 1 is the 31 moves you told me, isn't it, Blaze? Okay, wait a minute. I'm going to generalize this idea. What if I was trying to find Hn? Well, then I would do this recurrence, and I would end with the 2 to the n minus 1. And now when I use that geometric progression formula, my geometric series, I get 2 to the n minus 1. If I asked you, how long is it going to take to move 64 disks? You don't have to count 63 other numbers. You just have to plug in 64 to that formula. Plug in 64 to that formula. As I look at my notes, I am reminded actually that the original legend of this doesn't say they move one a day. It says they move one a second. That's in seconds. How many years? For the record, this is a little less than 50 times the life of the universe so far. We have plenty of time left, I hope. By the way, this number of moves is the optimal solution. This is a big O of 2 to the n problem, and there's no faster way to do it. On the other hand, if I add a peg, and instead of giving you 3 pegs to work on, I give you 4 pegs to work on. This is called partial version problem. There are my 4 pegs. If I move from 3 pegs to 4 pegs, there is no known formula for the optimal number of moves required. Doesn't seem like it's that big a change, but it's actually a huge change, provided you insist on using all 4 pegs. If you just ignored one and used 3, you'd be done in the same number of moves. Any recurring behavior in this fashion. Code word enumeration. You want to fix passwords and behave descending or ascending digits? I want to look at class schedules. How do I build a class schedule that provides the optimal number of rooms for the classes we want to provide? You've seen the course schedule for fall. Blah. Why? We only have so many rooms. We only have so many time slots. We only have so many people teaching. How can I fit them all in? What's the packing algorithm to fit all the talks I need into the fewest number of rooms? How many rooms do I actually need to fit all these talks? Can you do it in 4? Can you do it in 3? It's a scheduling question. All of these dynamic programming behaviors are recursively generated algorithms. By the way, recursively generated algorithms are small code-wise, which means they're easy to store. They're easy to write because they call themselves until they reach a base case. So they're very compact, and therefore they're very easy to incorporate into hardware. So doing things recursively is a beneficial idea. Question? I know I'm archaic and this problem is equivalently archaic. I'm going to send a real letter, a physical piece of paper mail. I need to go buy stamps. The stamp machine takes dollar coins dollar bills and $5 bills, won't take anything else. By the way, if this idea pisses you off, I stole this from the Easy Pass machine. If you actually drive down 66, when they used to take cash, the only cash they took were $1 bills and $5 bills and $1 coins. I pulled up with a $10 bill, I couldn't pay my toll. So, you go to pay for postage. You have to buy an even dollar amount of postage. How much is it going to cost? I don't care. How many different ways can you pay? Assuming order matters. Now you have a choice here. You have a choice on what to pick for your base case. What is the small amount of postage you can buy out of this machine? Buying an even dollar amount. This is a trick question. The smallest amount of postage you can buy from this machine. None. How many ways can you do that? One, we don't put any money in the machine, right? So my base case I put in no money. I'm buying $1 worth of postage. How many ways can I pay for it? There are two options here, right? Use a dollar coin or a dollar bill. I'll even write them like that. 1B, 1C. One bill, one coin. Keep going. Let's see if we can find a pattern here. And if we can find that pattern, let's see if we can abstract it. Because right here, yeah, I'm going to double this, right? I could pay with a bill twice. I could pay with a bill followed by a coin. I could pay with a coin followed by a bill, or I could pay with two coins. I did say the order mattered. So there are 4 ways here. And then here, I'll take each of those and put another B or another C after them. That's 8 ways. And when I get to 4, that should be 16 ways, right? But what happens when I get to 5? I need to double this, but I also need to add 1 because I need to add possibility of a $5 bill. What about 6? Like that? Why? Pay a 5 first, I'm left with the options for 1. Pay a 1 first, I'm left with the options for 5. So now I have a letter, a variable, I'll designate this. Pn is my payment for n. We know that P0 is 1. How do I write a formula? Pn. How do I write this into a formulaic expression? So what is it if n is less than 5? And then if n is bigger than or equal to 5, there's exactly what I wanted. How many different ways to pay $10? I'll be here for a while, right? I have to figure out the rest of it. I got to 6. When n was 6, we had 2 times 33 plus the number of ways to do 1. P7. Pay with a dollar or bill or coin. Then I'm left paying 6. Plus the number of ways to pay 2. How many ways were there to pay 2? because P5 was 33. If I ask you for P20, you're going to look at me like I'm a sadistic bastard more so than usual. So I don't want to do that. But I would like to know if there is a closed form for this idea. I'm not going to answer that question right now. But what I am going to do is I'm going to tell you that the idea can be generalized to any depth. So I'm going to add a new term here. What do you think that depth means in this case? If I say this is a recurrence of depth 5. Yeah.
Oh, say, better iteration of that.
Well, something changed every 5th time, but let's look at the formulaic version of this setup, right? There's my formula. Pn is given in its most general format by saying double the last one, but then look back 5. The depth here is how far back I have to go. So think about the Fibonacci problem with the rabbits. What's the depth of that problem? Because my formula only had me go back twice. The tower problem has depth 1. Now, there is a substantial difference between the rabbit problem and the tower problem. And as a matter of fact, the tower problem is also different from the stamp problem. In the stamp problem, I only ever looked at the numbers in the sequence, right? In the rabbits problem, I only ever looked at the number of rabbits, but in the tower problem, what did I have to do when I was done dealing with the numbers of steps? I had to add 1. This difference right here changes the method by which we find a closed form. But given that there are only 2 minutes left in today's class, I'm going to save the discussion for how to find a closed form for our next class, but that's not Monday. Because what are we doing? Yay. Please make sure you bring whatever formula sheets you wish to use from previous exams that already have my initials on them, and up to 1 new page of formulas. Again, same process applied. No worked out examples. If it says example next to the picture in the book, don't use it. No written out algorithms. We don't need them. But I will see you all then.